Swayam Prabha. Digital India. Educated India.
So today our special topic is going to be on social graph connectivity. Okay, so there is lots of studies in this direction about social networks, and there are specific problems. I will try to touch upon two problems. One in detail we will see, and the other one I will give it up to you to explore more. Okay, so the first problem is refining social graph connectivity by network augmentation. Okay. So, as the terminology suggests to you, we can just see that we want to improve the network's connectivity. Okay. But under what condition do we want to do that? Because obviously, if I want to improve network connectivity, a complete graph is an ideal case for me, right? But we don't have that privilege of having a complete graph, right, in social networks. Not everybody is connected to everybody else. One is that is not feasible, and the other one is we may not like to do that, right. I do not want to be known to everybody. I might have a smaller group where I would prefer to be noted for, like that. So, can I improve the network's connectivity for certain reasons? We will see what are the reasons that we would like to go for. So, one interesting motivation, I mean some of the motivation is, we know social networks disseminate information, like an information spreads very fast, right, in a social network. So, can I improve that? There may be certain things like some regional issues could be going on, but that might not spread to, say, in our national level. There are some problems that is happening that might be known only in the regional level, right. Whether it is in the North India or in South India, they might know only in that region, but they may not be well aware in overall India kind of thing. That is one kind of issue, and the other one comes in for marketing reasons. Okay. So, you might want to promote a product and you want it to be reached to n number of people, right, and you want to spread this information as much as possible and in less number of time, right. These are all certain problems that are there. So, improving connectivity drives up users engagement, okay, in the available online contents. So, everybody is like looking to I mean we want them to glued to the internet like most of the time. So, that is from the technology users side, they want to see how can I improve connectivity. Okay. So, if for example, if I have a Facebook network, we give these friend requests, you would have seen, right, you keep getting friend requests, suggestions, not friend requests, but suggestions for new friend addition, right. Those things also work in these based on these algorithms. Okay, what kind of new friend suggestion that I can give, so that that person should be relevant to you, right. So, this is also one more motivation that you can think of. So, as I said, one is viral marketing and the other one is content via online ads. So, you just want to promote whatever you are doing, right. So, what is the problem that we have here? If I want to talk about the specific problem, suppose we are given a connected, undirected, simple graph, okay, and a set of candidate shortcut edges. Okay. So, shortcuts. So, by candidate shortcuts, what I mean is, to begin with, every edge not in the graph is going to be a candidate shortcut for me. Okay. So, whatever graph I have set of vertices and set of edges, right. When I say I am going to improve connectivity, I can't obviously improve connectivity within the network, right, with the given number of edges. So, the idea is I want to add some more edges to this network such that the connectivity is improved. So, to add edges, where do I look for the edges? The missing edges come from the complement, right. So, the candidate shortcuts are nothing but the set of all non-adjacent pairs, right. So, you look into all possible pairs, all non-adjacent pairs of vertices, and of course, I cannot add as many edges as possible, right. I should have a restriction that I want to do. So, and we are also given an integer. So, the problem is given an integer and this candidate shortcuts and the graph, the original graph is given to us. Find a set, a subset of this candidate shortcuts, a set of how many edges we want, k edges. Okay, the k is nothing but the number of edges that we want, such that we have a utility function, we want to maximize that. Okay. So, the utility function here what we want to follow is based on an augmenting policy, we want to improve the characteristic path length of the graph. So, we will see the definition for all these things, what is the policy that we are talking and what about the characteristic path length that we want to improve on. Okay. Say for example, suppose we have this graph and I am talking about s equal to k is 3, say I have 3, I want to add 3 edges to this network. Based on some policy, I just need to add 3 edges somewhere in this network. So, something like this. So, if I add these edges, we can immediately see that connectivity of the network is very much improved, right. It is kind of more clustered, you will feel like all the nodes are kind of well connected, right. Basically here you will see that there is no cuttage in this domain, right. We have already killed the cut edges that are present here, like disconnecting that edge should also what to say, should not disrupt my network, right. Suppose somebody wants to leave the social media and he just suddenly shuts his account, then my network still should continue, right. All his friends should not be left out. So, that reason, that is also another reason. So, those things comes under the parameters that we want to improve in this study. Okay. So, what is a characteristic path length? We know path, right, between any two vertices you have a path. So, a characteristic path length is nothing but for every pair of vertices you take the distance between the pair and divide it over all possible edges, like n choose 2 edges. So, this is nothing but the summation over every pair of vertex and you look at the distance between them over n choose 2. Okay. So, this is the characteristic path length and we want to improve this characteristic path length. If I add some more edges, okay, into my graph, so that is what we meant here. By G augmentation, what we mean is after addition of the edges, this characteristic path length should reduce, then only my utility function will increase, right. So, and I want to optimize this quantity and how many edges should I add and where I should add, all those things plays a big role here. So, to also calculate a metric how much gain we are getting by adding these edges, we have this gain percentage or gain metric, which is nothing but the difference in the characteristic path length or actually percentage of the difference that we are taking. Okay. L of g minus L of g aug divided by L of g into 100. So, percentage, gain percentage, how much gain that we are getting by adding these new edges, right. So, k is going to be total shortcuts to be added and CS is, these are some notations. So, CS is set of candidate shortcuts and US is nothing but the utility score of the set S, right. So, coming to the augmentation policies, we have two policies, one is called as network centric and the other one is node centric policy. What is a network centric policy? Given k edges, I can add the, given a possibility of adding k edges, I can add them anywhere in my network. Okay. The distribution, we do not bother about where I have to add them. Okay. I just need to add k edges to the network and I have to improve my network's behavior. Node centric policy says you fix a number and to every node I should be adding these many edges. Okay. So, this becomes a node centric policy, that means that every vertex is getting kind of improved. The connectivity of every node is kind of improved here and I have to look for a uniform distribution of edges. The newly added edges is going to be kind of uniformly distributed. Right. So, there are a couple of algorithms that are existing. Okay, I will give now 3 existing algorithms we will try to discuss. So, what do you think the policy should be to improve this? It is a very fresh problem and it is not yet much results are there here. So, you can think of how can you do this, how can you overcome this problem. So, what we'll see that what are all the other things that we should improve along with this. So, one is the greedy algorithm. So, there are 3 algorithms existing. One is a greedy method, the other one is the random method, randomly you can just pick, and third one is path screening method. Okay, so, we will discuss each of these algorithms. These are well studied problems, so I can do it here also. Okay. So, what does a greedy algorithm do? So, I mean, do not look at this algorithm here written. So, if I have to add, what I should be doing, I should be looking at improving my characteristic path length, right. So, what I do is I pick up an edge, I add it to the network, and I calculate the characteristic path length, and I do this for all the possible edges, okay. And then we will pick out the edge which gives us maximum utility, right. So, this is a greedy one. So, this is for one edge, addition of one edge. After adding this edge, what I do the same thing, I repeat the same process by taking this second edge from the remaining set. You look for the best utility function, which edge is going to give you the best utility, and you add that edge, and you repeat this process k times, because we need to add k number of edges, right. So, it operates for k rounds, the greedy algorithm. In each round you add all the edges from candidate shortcut to the graph, one by one we do. So, take one edge at a time, you pick the edge and you check how much maximum reduction you can make, right, how much you can improve your characteristic path length, and you can see that this method will produce a local optimum in each round, right. So, and this is nothing but it gives you the upper bound. Greedy algorithm gives you the best solution, okay, best optimum solution. And what is the drawback here? You are going to do, suppose my graph is a very sparse graph, say I have 10,000 nodes, but I might not have 10,000 choose 2 edges, I might have hardly 20,000 edges in the graph or 80,000 edges, right. It is a sparse comparatively. When you compare with 10,000 choose 2 edges, 80,000 is going to be very sparse, right. This means what? I am going to do this to find the k edges, I have to operate on 10,000 choose 2 minus these 80,000 edges in the graph, right. So, it is going to be having a very long time to compute this. So, efficiency is very low here. So, it is not desirable in our case, because we want to do things in a very fast pace, right. If I want to promote a product, I cannot wait 10 days to find out whom I should add, right. I should be doing it quickly, because the product might lose its value, right. So, in this sense, greedy algorithm gives you a very best output, but it takes a long time. And what will be the best output here? If I add k edges, if I fix, usually, I mean, empirically what we have seen is, if we fix k depending on the policy that we are making, when we try to add these edges, usually the network is kind of reduced to a star topology, okay. Kind of they all become close. Every time it makes one vertex to be central, and because adding edges to that vertex will obviously reduce the characteristic path length. So, it always happens that there is one node which becomes central all the time towards the end of it, whether you add 10 edges or 20 edges, the addition is happening kind of to make your graph a star topology, okay. So, next option is look for random algorithm, okay, randomize it. So, by randomizing, what we mean is, this also again runs in k rounds, but what we do is randomly we pick two vertices. If they are already adjacent, leave them, pick another pair of vertices. If they are non-adjacent, just add an edge between them, okay. So, this will run in order n square, time complexity is order n square, and you will see that sometimes it will give you best result, sometimes it may not give, it is just randomly it is going to choose a pair, it will just add an edge, right. So, randomness or this random algorithm behaves as a baseline. When we said greedy algorithm is the best possible, it gives you all these optimum solution, because every round you are optimizing it, right. So, locally you are optimizing and then you develop on that, you get a global optimum there. But here we do not know about the optimality, it is just random and you keep adding randomly edges wherever possible, right. So, sometimes this gives good results, sometimes it gives bad results. So, we keep this as baseline to compare our algorithms. Usually random algorithm is kept as a baseline algorithm to compare, because this is highly efficient. We do this in order n square and this is the best possible time. Okay. So, the next algorithm is the path screening algorithm. So, path screening algorithm, if you see, suppose I want to add edges, it iterates over all pairs of vertices. Okay. So, you look into all pairs of vertices and you list down all the paths, okay. And there is also another delta parameter which is given to you, and you vary over a delta size window on this path. Okay. So, with the delta size window, what we do is we try to connect the shortest path. I mean, we are looking at shortest paths. So, take any path here, say suppose I look at this P1, what I do is we just add edge between, if suppose my delta is say 3, that means what? I look at every 3 window and I try to add an edge between the vertices, right. Because already we have shortest path, we know that we need, I mean these two are not going to be connected for 3 window. If it were already connected, I would have got a shortest path shorter than this, right. So, therefore, this is based on this window, delta size window, you keep adding, you look into all possible such addition of edges and then you choose the best possible. Okay. So, this provides utility score to the edge representing the terminal vertices of the window. Okay. So, what do we do here? So, utility score, you start from 0 for all pairs of non-adjacent vertices, you start with utility pair. Say suppose I look at a delta size of 2, then x1, x3, I should look for a possibility of adding an edge here, right. And then I have to calculate the utility score and my characteristic path length, I should see whether it is optimizing, and I have to do this check for every possible pair in this path. See, starting from the first path I choose, and out of this I will choose the best edge which I should add from here, and as I do this I will also update my delta. Okay. So, yeah, we add actually delta minus 1 to the utility score every time an edge is added, okay. An edge appears over there, and what is the drawback here? This is also like your greedy algorithm. Here you have to first collect all the shortest path and then you are going to run your algorithm, vary your algorithm over this delta window for every path, right, and you will be choosing the best possible k edges that you could add out of here, right. So, the time complexity for this algorithm is big O of c into n square into m log n. M is nothing but the number of edges. Okay. Excuse me. So, if we see all these schemes, I did not say about which policy we are following, right. So far we have not followed any particular policy, but these are all network centric policy, because I am randomly going to add, I just do not bother about where I am adding, right. In path screening can also be considered with node centric policy, like all these methods we could also restrict ourselves that at every node I have to add these many edges. If I make that restriction, then it becomes node centric. Okay. So, as long as my augmentation policy is not fixed, we will think of it as network centric, and in fact network centric works much better, because we are going to add it on the whole to the network. So, not only to every node, right, because that is not going to be feasible also, not every node will be interested to spread the information, right. If suppose we are talking about information spread in network, not everybody will be interested, and similarly if you give a friend suggestion for addition of friends, not everybody will be interested to add whatever suggestion you give, right. So, node centric sometimes it is not so good or not feasible in real life. So, we choose the network centric policy here. Okay. So, the next way, what is the next way method that we can try in improving these algorithms?